Come on. There we go. First thing you'll notice is that this is not your standard slide set from the publisher. These set of slides came to me from a former employee of New River. And I thought they were set up so well that I just discarded the ones from the publisher and used these. And I've modified them, of course, like I always do. So what's so special about gases? We know what a gas is, right, based on its physical characteristics, right? It needs a container, a three-dimensional enclosure to hold the gas. The gas will expand to fill any space it's placed in. And it won't hold its own shape and it won't hold its own volume. But from a historical perspective, gases were extremely important in chemistry because as the European scientists were coming out of the Middle Ages and they were starting to investigate physical and chemical properties, which is the way it worked at first. They were just conjoined. And anyone who was working in a scientific realm was called a natural philosopher. But gases were investigated first for practical purposes. Through the Dark Ages, alchemists had learned how to work with gases, how to trap them, how to condense them, how to place them together with other gases and react them. So all we needed to migrate into the modern era, into modern science, was a way to quantitatively measure these phenomena that alchemists had been working with for several hundred years. So we need to have a definition of what a gas is at the molecular level. Right. We consider gases as semi-independent particles. We say semi-independent because they're largely independent, but occasionally they do interact with one another. So we sort of hedge our bets by calling them semi. So gases are moving particles. They can either be atoms or they can be molecules. They can be combinations of atoms. All gases are miscible in one another. If you add any number of gases together in a container, they will form a solution, a homogeneous mixture every time, no exceptions, except for reactions, right? As long as they don't react with one another, then you'll form that solution. And it's actually stands to reason because there's so much space between the gas molecules, there's room for everybody, right? They don't need to exclude any other gases based on space, available space, because there's plenty of it. Gases do have mass, and we can measure that mass. In fact, let me see. I think we have, is it our last experiment? Yeah, the Dumas method. We're going to measure the mass of a gas in order to, using the Dumas method to determine the molar mass of a volatile liquid. We're going to vaporize it first so it forms a gas, and then once it's condensed, we'll weigh it. But you can weigh a gas as a gas. It doesn't have to be condensed. They do have mass, which means if a gas has mass, then where's that mass coming from? The individual molecules. So each molecule has kinetic energy. According to this equation, right? If it has mass and it's moving, that stands for velocity, then it has kinetic energy. So these gas molecules have energy, and actually what we do is we measure the average kinetic energy of anything, gases, liquids, solids, doesn't matter. We measure that as a temperature, and a temperature is a scale that tells us a relative amount, an increase or decrease in kinetic energy. Come on, there we go. They're always in random motion. We have to treat gases and all these molecules as if they were all in random motion. We know on an individual basis, each molecule has a trajectory and a mass, so it has energy, and it's moving a certain distance before it hits something else. So that particular molecule is not random. The problem is that there's so many of them, even with all the space that's in a gas, empty space, just a small sample of gas has billions of molecules in it. So for a practical matter, we treat gases statistically, like we do all matter, as a matter of fact. And that requires that we assume that their motion is random, because we can't track every particle. We just don't have the computing power. We don't have the detecting power to track every molecule. All right. So we're going to look at gases from a historical perspective. We're going to work through the gas laws, and the gas laws develop as technology becomes available to make the certain measurements that are required. And we're going to define what an ideal gas is. We're going to look at several equations and end up with an ideal gas equation. And one good reason to study gases is not just chemistry, but the air we breathe is a mixture. It's a solution, primarily nitrogen, 78% nitrogen, 21% oxygen, and about 1% argon, and then minor components, some of them pollutants. Carbon dioxide, plant food. So the Earth's atmosphere is necessary for life. If you're an autotroph, right, you take sunlight and you store it as molecular energy, like green plants are autotrophs, then you're dependent upon carbon dioxide. If you're a heterotroph, like humans are, and all mammals, then you require oxygen to take those stored energy molecules and break them apart and get the energy out of them. So one way or the other, the atmosphere is necessary for life. And there are pollutants. I'm not denying that. I just have issues with some people who try to make certain molecules pollutants that aren't pollutants, like carbon dioxide. EPA has been trying to make CO2 a pollutant forever so they can regulate it. That's their sole purpose.
Like whenever, like the exhaust gases that come out of the back of your car, they're not a pollutant.
Well, they're excess. And now that we have engine technology that is cleaner, and we have catalytic converters attached to your tailpipe, then we can spew out mostly carbon dioxide and water, and then nitrogen gas. The bad pollutants are the incomplete combustion products, like oxides of nitrogen. They can be really bad. And I guess all you have to do is pick a nice sunny day in California, like Los Angeles, and you'll know what pollution is. So I'm not denying pollution. It's just that some molecules are actually, I'll tell you what, I come from a background of agronomy, which is crops and soils. And I know for a fact that if the carbon dioxide level of the environment in which a plant grows is increased, then the plant becomes more productive. You get more biomass out of a plant that's in high CO2. And that's and through the Earth's geologic history, and we can recover some of these atmospheric gases usually trapped in ices. And we find out that many eons ago, the carbon dioxide level in the Earth, well, I guess in those conditions, it'd be hard to find ice, maybe at the poles. The carbon dioxide level was much, much higher, as much as 10 times as high as it is now. And that's where we get all the plants that eventually end up in coal beds because of excess production.
It's a plant with more carbon dioxide also produce more oxygen.
Mm-hmm. Yep. It does indeed. That's what do you call it? Waste product from green plant bioactivity. Okay. So I also take issue with environmentalists who want to blame global warming on humans. I mean, we do have an impact on our environment, but to the extent that some people say it, I don't believe it. And there are a lot of very competent scientists that don't believe it either. But they're being silenced. They're being ignored by scientists who are making money off of this research. Right? As long as the government is pumping money into it, or various governments around the world pumping money, there are people that are going to tell them what they want to hear. Right? Science isn't pure. Science is mediated by humans, which means it's susceptible. All right. So first we're going to discuss gases in terms of their physics. And then we'll get to where we can use what we learn about gases in chemical equations, stoichiometry. So if you want to describe the physical makeup or the physical behavior of a gas, you need to be able to quantify 4 factors. That is pressure, volume, temperature, and how much of it there is. N stands for moles. If you have values for each of these, then you can completely describe the physical behavior of a gas under most circumstances. So that was one of the first pieces of equipment that needed to be developed so that we could actually not needed to be, it was developed first and allowed scientists to investigate gases relative to volume. Volume was a given from the Dark Ages. They knew how to measure volumes of gases. Now we needed a reliable way to measure pressure so that we could quantitatively describe the relationship of a gas's pressure to its volume. Right. First, we needed something that would do that. So along came Evangelista Torricelli. He was an Italian, came out of the Renaissance, and he developed what's called a barometer. Now, barometer simply measures air pressure, and he used the technology of the day, which was very well developed, glass blowing. Right? Glass blowers were extremely competent at producing shapes, different shapes of definite sizes, and they could produce long, straight tubes of uniform diameter very, very reliably. So Torricelli took advantage of that. And for all I know, Torricelli could have done it himself. Or he could have gotten a long glass tube and all he had to do was fire the end and close it off. And then he filled the tube with mercury. That's a very dense liquid. And here's, okay. So he had this tube that was open at one end. And of course, it was open end up like this so he could fill it with mercury. And then he just capped it off with his hand or his thumb and then inverted it and submerged his hand in the mercury. They didn't know about mercury poisoning back then. In fact, some people thought it was the elixir of life. Surprise, surprise. So there, once he submerged this tube in that mercury and he left the top of it open to the atmosphere, and he was, at some point in his investigations, he came to the conclusion that the atmosphere full of these gases was bearing down on the surface of that mercury. Because when he turned his thumb loose, the mercury dropped, but it didn't go all the way down to the bottom. So he couldn't blame it on something pulling the mercury up because there was nothing up there, right? He had just created the first vacuum. So what was holding it up, he reasoned, was pressure from the air in the Earth's atmosphere bearing down on the outside of that pool of mercury, and the pressure being distributed and forcing mercury up that tube. It was supporting that column of mercury. He noticed that if he took his barometer and went up a mountain, it would drop. And he reasoned that that was because now that it was higher in the atmosphere, there was less atmosphere above him to press down. And if he went down to the ocean from his current elevation, it would go up. So that was a way of measuring air pressure. And other people got interested in his invention, and he and others would just set the barometer on the desk and watch it. And they noticed that when the weather started to get bad, it would drop. Air pressure would drop. And when the storm passed and the sun came back out, the barometer would be on its way up again. So they associated bad weather with low pressure and good weather with high pressure. And we still do that today. All weathermen, they put these L's and O's on their maps and show you where the systems are. And the very lowest air pressure that you can measure in a system is in a, well, you can measure it in a hurricane. I suspect that you could also measure it in the center of a tornado, if you could get in there and measure it. But definitely hurricanes will have very, very low air pressure at their centers. Okay. So there, we could use it to predict the weather. And okay, now before I talk about the different ways to express pressure, this barometer could also be modified. There's your mercury, and it's up here somewhere. Could also be modified to measure the pressure of a trapped gas. All you have to do was seal this off, right? Seal that off, and then put a tube here into the container of the gas, and it would press on that mercury and deliver its pressure in such a way that you could measure that height of the column. That's called a manometer. And then the medical profession got hold of it, and they added a prefix to manometer, the sphygmomanometer. That's the one with a cuff they wrap around your arm, and you can measure your blood pressure with it. Because as it, say your arm goes through here, and as it pulses from the arterial pressure going up and going down, then it will press on this, and you can see that mercury jump. Well, if you increase the pressure so high that it doesn't jump anymore, and then you start releasing the pressure, then it'll come to a point where it'll start jumping again. And then it'll jump and then go down, and then it'll stop jumping. So the systolic pressure, the diastolic pressure are what you will measure as your blood pressure. And of course, it works better if you've got a stethoscope and you stick it under the cuff and you listen for the Korotkov sounds. Right, when it first starts doing that swishy sound, that's the high pressure. As you decrease the pressure in the cuff, And then when it finally goes away is the last Korotkov, and that tells you the low pressure. And you read it when you reach those. That's what they're listening for, if you didn't already know that. There are actually 5 Korotkov sounds that are unique, but the only ones that I'm interested in are the high pressure and the low pressure. Okay, how do we express pressure? Well, if we're at sea level, what's accepted at sea level, on average, right? It'll go up and down with weather, but on average, the distance here to here at sea level is 760 millimeters of mercury. And that's considered 1 atmosphere of pressure. Okay, so we have an equivalence here, and equivalence means we have a conversion factor. So if we have a barometer and we measure this in millimeters, we can convert that to how many atmospheres it is. Here's an example from the Raleigh County Airport. 694 millimeters of mercury at about a half mile up. So it's going to be lower than an atmosphere, obviously. And we do our conversion factor thing, dimensional analysis, and we end up with 9/10 of an atmosphere. Okay. And if you go down the road and head up to Winter Place, where you're going up another 1,000 feet, and on the same day measure a pressure of 0.88 atmospheres. And if you went to Denver, it'd be even lower than that. Wait a minute. Yeah, because Denver's a mile high. Okay. And here's an example converting atmospheres to millimeters of mercury. Air pressure or gas pressure is one of those things that has a whole host of different ways of measuring it. These are just 2, millimeters of mercury, atmospheres. Anybody that's taken their own tire pressure knows pounds per square inch. Yep. So we can also equate that to 14.69 pounds per square inch. And in fact, the definition of pressure is a force per unit area. That means it is an intensive property. It doesn't matter how big your tire is. If it has 36 pounds per square inch in it, it could be this big or it could be this big. I had a bicycle. I rode a 10-speed for a while to go to college, and its tires were up 85 pounds per square inch, 85. And that's not nearly as high as they can get. Some of those racing tires that are like this, they're like 120 pounds. So really, I had to watch out for 2 things in riding my bike in the city of Atlanta: other drivers and storm grates, because the grates were this way and they had to slide that way. If you could go right into one, so I'd have to go on with this, dodge it. But that was when I was first getting started going to college from home. I was only 3 miles from 5 Points, and I was going to Georgia State University, which is right downtown. And parking was free for bicycles. And I also noticed parking was free for motorcycles. So it didn't take me long to save up money and get a motorcycle. Okay. Pressure can be expressed in different ways. The SI unit for pressure is the Pascal. And the Pascal is a derived unit from another derived unit and a fundamental unit. So a Pascal, 1 Pascal is equal to a force of 1 Newton per square meter. So square meter is derived from the fundamental unit of meter, and the Newton is derived from Newton's second law of motion, which is F equals ma. So any mass that is experiencing an unbalanced force will accelerate that fast. its speed will increase over time by this amount. So a Newton here, this Newton of force is equal to mass of 1 kilogram, right? Accelerated at a meter per second squared. Okay. So kilogram meter per second squared is a Newton. And the nice thing about SI units is they're all interconvertible. If you know what they're equal to, like we know this one's equal to that, we know this is equal to that, then if you need to do a calculation where units have to cancel, then the SI units are probably your best bet. But for our purposes and for practical purposes, we're going to stick with millimeters mercury, atmospheres, PSI. They're older than the SI system, actually. Okay. Oh, and inches of mercury. So this is equal to 1 atmosphere is equal to 29.92. Yeah, 2992 inches of mercury. The barometer I have in my lab in Beckley reads out in inches of mercury. So when we do our experiments down there, when we do the Boyle's law down there, we have to convert to atmospheres because it works better.
Do they have one here?
No, but I got one on my phone now. Yeah, I can read off the atmospheric pressure. We'll need to know the atmospheric pressure in order to do this experiment. And I'll explain that in a minute when we talk about Boyle's law. Okay. The bar is another measure. The bar is equal to so many pascals. Millibars are probably more commonly used, especially in weather. If you see a detailed weather map, it's got lines all over the place. It's got isobars. Right? So those lines follow the equal pressures. Right? And they're the numbers that are associated with those lines are in millibars. We're not going to mess with those. That's just information. Okay, so we can convert PSI into inches of mercury, just like that. All right, so we have a chained conversion, like we studied earlier on in this course. We can convert millimeters of mercury to millibars. Right? We just have to chain the conversion factors together with the ones that we know. And that millimeters of mercury is 957 millibars. And when they're reporting the pressures of hurricanes, it will be in millibars. And they'll be down in the 800s. They'll be really, really low. All right. Let's see. I'm going to have to move along pretty quick here. This slide simply converts a column of mercury that high and the diameter of the tube it's in, and just proves that millimeters of mercury is a valid expression of pressure. Okay, first law, Boyle's law. So Robert Boyle came along not too long after Torricelli invented his barometer, and the idea was disseminated. So Boyle used a barometer, but he also created a device where he could study the relationship of pressure to volume of a gas. And in order to do that, you have to hold these two constant temperature and constant moles. Fairly easy to do because the experiment only lasts a few minutes. And when you see how he did it, you'll understand that he held the number of moles constant also. He used a J tube like this. Right? So he just had to take a long tube and bend it into a curve. And then he added mercury to it. And of course, when he added a little bit of mercury, it'd pool up in the bottom, add a little bit more. And then once he had it enough to where it touched the inner wall here, that trapped the gas in there. Now he has constant moles. And the experiment didn't take very long, so he has constant temperature. Okay, so he kept filling it up, and he noticed when he got, enough mercury to fill it up to here, over here, it only went up that high. So he reasoned that there was something in there, the gas was pushing back and keeping it from, it was compressing the gas, and the gas was applying a force against the mercury that was holding up that height of mercury, okay, in so many millimeters of mercury. Well, he also reasoned that it wasn't just this mercury that was pushing down on it, but he had atmospheric pressure also. So he had a barometer over here on the side to measure the atmospheric pressure along with it. And since these tubes are uniform diameter, then he could equate height to volume, right? If the diameter doesn't change, then right the volume of a cylinder is height times its area. So if the diameter didn't change, then the area doesn't change. So V is directly related to height. So this took place in the middle of actually he did his experiments soon after the barometer was invented. But he published his work in 1662. And this became known as Boyle's law. What he showed, and we're going to show in this plot, is that if you have pressure and volume plotted together, right, you put so much pressure in terms of the height and the atmospheric pressure, you get a value there, and you measure the volume. And then you add more, and you get more pressure, and you get a lower volume. So as this gets bigger, that gets smaller. Right? It's inversely proportional. Right? You remember that from our graphing experiments. So these are just some data points that were invented to illustrate. 25 atmospheres, you get 4 liters. 20 atmospheres, the gas starts to expand, and you keep going and going, and you get this plot. Okay. Well, on this plot where you have pressure and volume, what's the independent variable? Well, on the x-axis, the pressure. Yeah, pressure. And the volume is the dependent. And what you get is a best fit curve that looks like that. In mathematics, that curve is called a hyperbola. And if you remember from math, a hyperbola has a special characteristic. It never touches the axes. Well, in the math class, I remember on the full Cartesian system, you'd have a mirror image over here. But we're only interested in this part. So Boyle reasoned from this data that pressure times volume is a constant value. Whenever you have this relationship, the product of two variables equals a constant, they're always inversely proportional. In order to keep that constant, if pressure goes up, volume has to go down. And what would happen if this one actually touched out here? It would have to touch when volume is 0, right? If volume is 0, that destroys your relationship, right? 0 times anything is 0, so you don't have a constant anymore. So it just keeps going to infinity, getting closer and closer to the axis and never touching it in both directions. Okay, so Boyle published that work, and it's not very useful here unless you know what that constant value is. Right? In our example, the constant value was 100. But it's more useful to express this in terms of what happens before and what happens after we do something. So if we have a pressure and a volume, and it's equal to a constant, and then in the same experiment, we change the pressure and we get a different volume, but they're still equal to that constant. So this is a case in math, I forget the proper term for it. If A equals B and B equals C, then A equals C. So if that equals that, and that equals that, then they're equal to each other. So P1V1 equals P2V2. I call that before and after. If you know the conditions before and you know one of the conditions after, you can solve for the third one. It's like any algebraic expression, one unknown, you can solve for it. We don't do two unknowns because then you need two simultaneous equations. And I don't go there. Not in the real world. Okay, so we're going to use that pattern for the other laws. Right? This before and after type of approach. So that was Boyle's law. All right. So these are various examples solving the equations, and we don't have time to do it right now. But I will point out that as long as the pressure is measured in the same units, it doesn't matter what they are. As long as the volume is measured in the same units, it doesn't matter what they are because they're ratioed anyway. All right. So here's another example with cubic feet in PSI. All right. It still works. Then along comes Charles. He was a Frenchie. Charles' law. That's the way I do it. Nowadays, I think it's proper English to add an S on the end of that. Charles's. Go figure. I left the apostrophe off in this one anyway. So what Charles did was he investigated the relationship between volume and temperature of a gas. That means pressure has to be constant and moles have to be constant. Okay. So in order to do that, he had to have a reliable way and a system for measuring temperature. And early on in the course, I think we talked about the three main types of main systems of measuring temperature. Fahrenheit was first, then Celsius, and then Kelvin. Okay. So once a thermometer was invented to make those measurements, then Charles could pursue his line of research. And what he discovered was, well, Charles did the work, but he didn't publish it. There was another Frenchman, Gay-Lussac, who was working with physics and chemistry, and he took Charles' experiments and applied them to his work. And when he published his work, he gave Charles credit for it. So that's why we put Charles' name on it. Volume and temperature relationships. So if you measure temperature and volume, what you find is that as temperature increases, so does volume. So they're directly related. Let's see, do I have another one in there? Okay, so we get this straight line effect. So what we have is volume divided by temperature is equal to a constant. So whenever you have a quotient of two variables equal to a constant, they are directly proportional. As this one goes up, that one has to go up in order to keep this constant. And then we can do the same thing here, 1 here, and this is 2 here, and set up a before and after situation. There's just one fly in the ointment. Notice that our line stops where the temperature is 0. With Celsius, you can go negative. If you go negative in this formula, it won't work anymore. Right? It's kind of like that zero effect for Boyle's law, the negative effect for Charles' law. So what we need is a temperature that is always positive. That's Kelvin. because Kelvin moves the 0 point down to absolute zero and there's nothing below it. That's a theoretical point, actually. Right? How would you get 0 Kelvin? How do we make things cold? Let's look at it that way.
Go out into the complete blackness in between galaxies where there's almost no matter. And then take the temperature somehow.
And it'll be about 4K. Yeah, that's background radiation. It's been measured. The way air conditioners and freezers and refrigerators work is they take the heat from one enclosure and dump it someplace else, which is at a lower temperature. Lower temperature of the fluid that's being used to extract heat. So we can't get to 0K because there's no place you can dump the heat. There's nothing colder than that. So we're never going to get to 0K. Not on a massive scale, right? Some scientists have claimed they've reached 0K for individual molecules. There's absolutely no motion at all. So they fire a laser at just the right frequency and just the right power at a molecule approaching, and it stops it. Technically, that's 0K. Anyway, Charles did these experiments, and Kelvin was working in this time period with the emerging science of thermodynamics, because the steam engine had been invented and they were trying to make it more efficient. So they're trying to understand what is it about this heat flow that allows us to extract energy from it. So there were a lot of people working on it. Sadi Carnot from France made the most progress. And Lord Kelvin was interested in it. And I got a reproduction of his paper where he talked about this new temperature system he was proposing. And it was based upon thermodynamics. But a simpler explanation simply takes this gas and we extrapolate that line down to a point where we get 0 volume of our gas. An ideal gas should be 0 volume at 0K.
So was 0 Kelvin back in their day different from our 0 Kelvin?
Nope, it's exactly the same. Well, it's been refined, you know, what is its relationship to Celsius. Now we, let's see, 0K is equal to a negative 273.1, I think it's 7 degrees Celsius. Okay. So they'll keep working on this and refine these digits out here. But this part is what we're going to use because it won't change.
So he just came up with like that number, just like
With his research, yeah. So this is the explanation. If you extend that line, extrapolate that line to 0 volume, you reach a point on the Celsius scale at minus 273 degrees. So if we set up a new scale with 0, then when we get to 0 Celsius, we're at 273K. And that's the relationship. If you have K equals Celsius plus 273. All right. So we can solve equations like that all day long using I and F is initial and final. I use 1 and 2 because it's easier. So you can just solve it for your unknown and rearrange this before and after equation however you want. As long as you keep moles and pressure constant, it works. Okay, and these are other solutions, and it only works if your temperature is in K. So if you anticipate a problem is going to require a gas law that incorporates temperature, always convert it to K before you do the calculation. All right. So the last law I want to talk about as an individual comparison of two of these variables is Avogadro's law. And the Avogadro experience was similar to Charles. Avogadro was an Italian. And I think I may have expressed this one before. But Avogadro was looking at the relationship of volume and moles. So this is constant, and this is constant. And what he discovered was as the number of moles increases, the volume increases. All right, so it's another direct relationship, like Charles' law. Only Avogadro taught this to his students. One of his students his name was Cannizzaro, who became a teacher and wrote a chemistry textbook based upon Avogadro's understanding. And so Avogadro didn't publish it. Cannizzaro gave him credit, and that's why we attach his name to it. Well, I don't have time to go through the whole story, but chemistry was in chaos in the early 1800s in Europe, because they based all their stoichiometry, their reactions were based upon mass. They didn't understand that reactions were atoms and molecules, numbers of things. So Avogadro's law gave them the ability to to make the jump from mass to moles. And I may have described this before. If you have two gases, right, like that, do this one, they have the same volume, they have the same pressure inside, and they have the same temperatures inside, then they have to have the same number of particles inside, regardless of what they are. Doesn't matter. A gas is a gas is a gas. And if the gases are made of different materials, like this one may be methane, and this one may be, well, I don't know, just oxygen. So oxygen's going to be, let's see, well, oxygen's going to be heavier. So they have the same number of particles, but this one's heavier than that one is. And the explanation for it is the fact that the individual molecules and atoms are heavier than in this one. So that's where they made the jump from mass to numbers. And that solved a lot of problems.
So how did they measure? I think.
Balances. Yeah. Yeah, they had very, very accurate analytical balances that were mechanical. In fact, when I first started college, we had analytical balances. They were these big green machines made by Mettler, right? And they were mechanical, and they would measure down to 4 decimal places of a gram, like 1/10 of a milligram. They were a pain to use, right? As compared to electronic balances now, which are dependent upon a different mechanism. But they worked. And all you had to do was maintain them properly. You know, have them set on they had a big table that was a huge slab of marble. It was mass ballast. So it would, and on rubber feet. And our balances were set on those. And they were in enclosed rooms. So if you had to weigh something, you go into the room. And you could measure down to very small amounts. And I imagine that even at this time, they had mechanical balances that would go down to 6 decimal places. I used to have an electronic balance that would go down to 6 decimal places of a gram. So yeah, they could measure with very high accuracy gases. Okay, so we can do the same thing with this one we did with Charles, like V1 over N1 equals V2 over N2 And that's the useful form of Avogadro's law. Okay, I'm going to skip through these, except we'll stop here. Now we can apply the gas laws to stoichiometry. Because if we have a balanced equation, and in this case, they're all gases, right? Ammonia, nitrogen, hydrogen. This is the reverse of the Haber-Bosch process. And we know that the relationship here is 2 moles of ammonia makes 4 moles of product gas, like 1 nitrogen and 3 hydrogens. So the ratio of the gases to one another is 2 before and 4 after. Right? So we have 2 before and 4 after. So if we have a volume here and we have these, then we know the volume that should come out of that reaction. So what's our starting amount? 35 cubic feet. If it starts out at 2 moles and 35 cubic feet, if it comes to 4 moles, it should occupy 70 cubic feet, right? Twice as much. All right. Now, a more useful arrangement is not just to confine ourselves to holding 2 of these constants so the other 2 can vary. I mean, that's useful sometimes, sure. If you have the conditions where it's the case, but suppose you've got all 4 of them varying. So we're going to create a combined gas law that allows us to solve for one if we know all the others. So we're going to start with Boyle's law, like P1 V1 equals P2 V2. Right? Then we know that the relationship between volume and temperature is Charles' law. And then we know volume to moles is Avogadro's law. So there we have our combined equation. P1 V1 over N1 T1 equals P2 V2 over N2 T2. And all we have to know to solve for one of them is 5, 6, 7 others. All right, that gives us a way of dealing with it. Now, this is also going to be a constant, right? These are all equal to a constant. Just like the individual laws, the combined law is equal to a constant. Well, now suppose, rather than knowing before and after conditions and solving that equation, suppose we're in a state situation. A state function says, this is where we are right now. These are the conditions we have right now. How are you going to solve that one? Well, you just have to be strict about your units. If we take this one, PV over NT equals a constant, and we set these units 1 atmosphere here, and 1 mole here, and standard temperature, which with gases is 0 degrees or 273 K. And then we measure the volume under those conditions, and we find out it's 22.4 liters for any gas. Then we would combine all of these, we get 0.08206 liter atmospheres per mole K. Right? And we give it a special symbol, R. That's the ideal gas constant. With these units of measure, if you change the units of measure, that number will change. Right? So as long as your pressure is in atmospheres, your volume is liters, temperature is K in moles, then you can use this in the equation. And it's usually written in a linear form. It's just rearranged like that. PV equals nRT. So now, if you know the pressure, the volume, and the temperature of your gas as part of a chemical reaction, you can calculate the number of moles. That's the ideal gas equation. Now, what's an ideal gas? An ideal gas is defined as doing these certain things. It remains a gas under all pressure and temperature conditions. All the way down to absolute zero until there's nothing left. Right? We know that doesn't happen, but that's our ideal. It has a point molecular volume. Remember from geometry, what's a point? It has no dimensions, right? A point has no dimensions, no length, no height, no width. But if you make a line, that's one dimension. If you make like a box, that's two dimensions. And if you make a cube, say, that's three dimensions. Well, gas molecules are treated as if they had no dimensions, right? So the volume of the gas molecule doesn't get in the way. It has to be that way if it's going to be zero volume at absolute zero. And they don't interact with one another. In other words, they do impact, right? You do get molecules banging up against each other and banging up against the walls of the container. But they don't interact. In other words, they don't attract and they don't repel. They just act like billiard balls. When they come in like that, they smack and go off. Just conservation of momentum. And they obey all these gas laws. That's an ideal gas. We know real gases don't do that. They liquefy, or some of them solidify as we make them colder, like dry ice, like solid carbon dioxide. They do have actual volumes and masses, and they do interact with one another. And that's how we explain certain physical behaviors and chemical reactivity sometimes, is how they interact with one another, attracting or repelling. And of course, they interact with the walls of the container. If they didn't do that, we couldn't measure the pressure. Now, under what conditions do most gases behave ideally so that we can study them as if they were ideal? Under conditions of high temperature and low pressure. And low pressure also implies low moles. All right, so I won't put that one up there. High temperature, low pressure. Under what conditions do we find gases obeying those rules? High temperature is relative to absolute zero. So 273 degrees Kelvin, not degrees Kelvin, it's just Kelvin, 273 K is high temperature. All right, so gases in this environment, they're good to go for temperature. How about pressure? Low pressure is 1 atmosphere, or less than, say, 20 atmospheres. It's low enough so that they behave ideally. And this is practically determined. All right. So this particular equation was proposed by Emil Clapeyron. You'll see that name again if you stick around for the second semester. In 1834. Now, the units we used before, this liter atmospheres per mole K, gives us this number. If we use different units, and the units for the SI units are pascals, cubic meters, mole K. A pascal times a cubic meter is equal to a joule, which is an energy unit. Sometimes we have equations that require injecting energy terms into them. So in that case, we'll use 8.3145 joules per mole K. In fact, we're going to see that a little later in this slide set, if I don't run too long. Okay, let's see. So you can do various arrangements of this equation, this state equation. So you got two situations for solving problems with gases. You got the before and after situation. And if you read a word problem and you see volume conditions here and the volume changes there, and maybe temperature conditions and the temperature changes, and he wants to find the pressure, then you know you've got a before and after situation, and you can use the combined gas law. But if it says these are the conditions, pressure, volume, temperature, how many moles? then you know you're in a state situation. You don't know how you got there. You have to use the ideal gas equation. Or you can actually ratio values. Say if you want to find the ratio of moles to volume, that can be done also. Okay. Right, I'm gonna have to skip this one. Just move along really fast. These are conditions where you're only given the state at that point, and you have to calculate some other factor, right? If you know three of them, of course, the constant's always there. And if you know three of the others, then you can calculate the fourth one. But you have to be sure that your units match up. If this is your constant, you got to change your units to liters, atmospheres, moles, K. Otherwise, it won't work. All right. So let's see. Here's a stoichiometric problem. We're gonna look next week. I'll be here, so we're gonna look at some of these problems in the review document. So dig into the review document and work some of them. I know there are a lot of them there. That's just the way I work. Just do the ones you can get to, say all the even ones or all the odd ones, whatever you have time for. And we'll talk about it in more detail next week. Okay. Or if you want to see more extensive discussion of this, I've put the link to my 101. My Chem 101 class is parallel to this one. And I put the link in your Brightspace, so you can go to that one. And it has I'm in more detail, right? The stuff that I'm skipping. This Dumas method, we'll talk about this in much more detail when we get to that experiment, but it simply combines these two equations. Where are they? All right. It combines the equations for molar mass, which I abbreviate MW for molecular weight. We used to call it molecular weight. Now it's molar mass, but MM just doesn't sound the same. So molecular weight is simply the mass per unit of moles, right? And then PV equals nRT is how you find out that number of moles. So if we solve this one for PV over RT, and then we take this and put it in there, and then solve for molecular weight, cancel terms and so forth, then you get an equation where you can use the gas law to calculate the molar mass of your volatile liquid. And that's what we're going to do with the Dumas method at the end of the semester. All right, so I have to skip that one. Here's another problem that you'll have to look at the other. You have to look at the other video to get all the details here. Sorry. I wanted to get to Dalton's law of partial pressures. John Dalton, he was the same one that proposed the atomic theory. So he wasn't consumed with one line of work. All Dalton's law of partial pressure says if you have a mixture of gases, a solution of gases, and you measure the total pressure, that total pressure is going to be due to the pressure of all the other individual gases. Arithmetic total of the pressures up to however many you have. Okay, so if you could separate the separate gases under the same conditions, this gas would give that pressure, that pressure, that pressure, and you add them all together, you get the total. That doesn't seem like a big deal until you equate the pressure to using the ideal gas equation. Solve the ideal gas equation for pressure and you get nRT over V. And if you substitute nRT over V in each one of these, then you get something that looks like this, right? And notice that we can factor out, right? What stays this, what is variable in that equation? The moles of each of the gases. The R is the same, the T is the same, the V is the same. You can factor those terms out just like we do in algebra. Right? And when you do that, let's see. Yeah, for example, N1 equals P1V over RT, so forth, so on. And you collect your terms. And we find that the total moles, these pressures are, the factor that's responsible for these different pressures is the number of moles of each of the gases in the mixture. Right? So we come up with a new expression for how much of each gas is in there called the mole fraction. We know the total number of moles of gas in the container, and the mole fraction is just this gas's number of moles divided by the total. It's a fraction. And if you add all the fractions together, you come up with 1. Okay, that's what that X means. So if we do that, then the pressure of each gas is equal to the mole fraction of that gas times the total pressure. And here's an example of what you can do with it. This molecule on the left is nitroglycerin. This balanced equation shows the explosive decomposition of nitroglycerin. 4 moles of nitroglycerin produces 29 moles of gas. That's where the explosive force comes from. It just that fast goes from 4 to 29, right? So the pressure goes sky high and you get an explosive effect. And sometimes when you don't want it. This experiment is conservative, right? It uses a 100-liter vessel at 25 degrees and 20 millimeters of mercury. So the vessel has been partially evacuated. And then we put some nitroglycerin in there. And afterwards, we find that the vessel has increased by 10%. Temperature's gone up to 400 degrees Celsius. And the final pressure, the total final pressure is we can calculate based upon these conditions. Okay. And this is using the combined gas law. And in the mole terms, the before terms is 4 in the denominator and the after terms 29 in the numerator. Then we can find out that the final pressure is 297 millimeters of mercury. It went from 20 to 297 in an instant. We're not going to stop there. We're going to say, okay, how many millimeters of mercury can we blame on carbon dioxide? Well, the stoichiometry of the equation tells us the ratio of 12 to 29 is carbon dioxide's contribution, 123 millimeters. Water's contribution is a ratio of 10 to 29, and so forth on down. And if you add up all those contributions of pressure, you should get the total. Add them all up, and you get pretty close to the total that was measured earlier. Okay. All right, so what theory controls all of this? I think this was Dalton's doing also, the kinetic molecular theory. This is a general model that simplifies our understanding of how gases behave. And molecular means that they're individual particles moving around, and kinetic means they've got energy. That's all that means. But here are the postulates. Large numbers of particles, right? The particles are small compared to the distances between them. There's lots of empty space relative to the size of the particles. They're in constant rapid motion, and they're the random motion, actually. They collide with each other. That's inevitable. And they collide with the walls of the container. That's how we measure pressure. And when we measure the temperature of this gas, the temperature is an expression of the average kinetic energy of all the molecules. Now, we understand that some are moving faster than others, some have different energies, but overall, when we average the energy out, we get a certain temperature. And we have to assume that the molecules don't interact with one another. I'm about out of time. Okay. I'm going to let you look at the other video to get this one. What we're doing here is we're taking 7 bowling balls. They're 5 kilograms each, right? Which is what, about 11 or 12 pounds, something like that. So it's a kid's bowling ball. What is the standard for 14 pounds? Or is it 12? 12, okay. So we're close. And we're taking different velocities. Say we have these 7 balls and they have different velocities listed down the left-hand side. And we're calculating their energy based upon kinetic energy equals 1/2 mv squared. And then we're taking their velocities and we're averaging them. And if we do an arithmetic average of their velocities, we get 40 meters per second. Well, if we take 40 meters per second and try to calculate the energy, well, actually, we're going to average the energy first. And we get 5,000 joules if we average the energies. If we try to calculate the energies using 40 meters per second as the average, then we don't get 5,000. Right? What we end up with is 44.72 meters per second will give us 5,000, right? Not 40. So the average velocity is not the arithmetic average of the individual particles, but instead, our mathematical approximation is closer if we use a procedure called root mean squared. So in order to do that, we work from this end. We take the velocities and square them. And then we take the mean of all those squared velocities. And then we get rid of the square by taking the square root of it again. And if you do that, square, mean, and then take the root, you'll get 44.72. Now, root mean square, we use that all the time, every day. Right there, out of that. Well, not here. Where's a wall socket? Right over there. Out of that wall socket, we get what, 120 volts or 115 volts? That's the root mean square of our sine curve of voltage in that thing. It's alternating current. So it pushes this way and then it pulls and pushes that way. Goes back and forth. And the root mean square voltage, what's coming out of there, the high voltage is closer to like 160 at its peak, but it goes through this sine curve. So our root mean square gives us the equivalent of direct current. Direct voltage is 115. All right. So we would have to know the direction and the speed of every particle in 3 dimensions. That's what that means there, X, Y, and Z. And the root mean square is simply that expression, the square root of the mean of the squares of the velocities. Right, this is more important. The root mean square velocity can be equilibrated to this expression, 3 times the gas constant times temperature divided by the molecular weight of the molar mass. And that's the root mean square velocity. Okay. This has to be in Kelvin. This has to be 8.3145, has to be the one with energy unit. And this one has to be in not grams per mole, but kilograms per mole. Because these are all fundamental SI units. So this one has to be in, if you're solving for that one, it'll come out kilograms per mole. If you're entering it in to find something else, you have to convert into kilograms per mole in order for it to work. All right. So I'm going to have to skip these. This is a comparison of two gases. The heavier gas moves slower, the faster gas moves quicker from one end to the other. And in this case, hydrogen chloride and ammonia put into the end of a glass tube will meet and form ammonium chloride solid, and it'll look like a fog. So when it does that, the ratio of the distances traveled is 1.463 based upon that equation. And I've seen this demonstrated before. It's pretty cool. All right. And you can use this to determine the molar mass of an unknown simply by comparing it to a known and measuring the distance traveled. Graham's law, that's Graham's law that we were just discussing. I'll just end by saying this phenomenon, this Graham's law of effusion, was used to concentrate U-235 during World War II to try to make enough concentrated U-235 to make a bomb. Right? It needs to be about 95% U-235 to get a chain reaction in a bomb. So one of the ways they converted it was they had this big factory. I used to live here, and we would drive around that factory for entertainment. Couldn't go in because the guards there were shoot first and ask questions later. So most of the floor space in this factory, which is about 40 acres, is taken up with diffusion cells. So you have your gas with U-235 and U-238, which are the majority isotopes. You want this one. This one's only about 0.7%. It's very small. It's not too big. So you have to get it into a gas, right? Uranium is a metal. So to get it into a gas at a reasonably low temperature, they converted it to the fluoride, the hexafluoride. Now they can make a gas out of it. Once you got it in the gas state, you run it through a partition with very, very, very small holes in them. And the U-235 is going to go faster. So it concentrates on the next side, just by a tiny amount. So you keep pushing it through more and more of them, and it gets concentrated, more concentrated. That's why we need this 40-acre building, because it's mostly taken up with these filters. The trick was finding a filter that would not succumb to fluoride corrosion. Couldn't use stainless steel, right? It would eat it up. So as it turned out, I said, oh, I don't have it there, do I? I missed it. Yeah, I missed it on this slide set. DuPont. I can't remember the scientist's name, but in the middle 30s, this scientist came up with the first fluorocarbon plastic, Teflon. Okay. Turns out Teflon is impervious to this stuff. So the trick was engineering the panels so they had very small holes in them. Once you did that, you could just stack them in there, thousands of them. And at the end of the chain, you come out with 95% U-235. You just have to convert it back to the metal and judiciously, in small amounts, separated from one another, right? You don't want critical mass. And then allow the scientists at Los Alamos to build the bomb. That turned out to be the one that was dropped on Hiroshima, little boy. That was a uranium bomb. They were also working on another one composed of plutonium. Plutonium is man-made. You don't find it in nature. So you have to make it in a nuclear reactor and then do something similar to concentrate it, separate it from the other components. And then the trouble with plutonium was you couldn't make a gun out of it. In other words, you couldn't do like a little boy and fire a slug of uranium, add another slug of uranium with an initiator incorporated to set off some neutrons, and then it would just blow up. They were very confident. They didn't even test that one. But plutonium, if you did that with plutonium, you get what they call a fizzle, right? You'd have a sizable bang, but it wouldn't be a nuclear bang. So they had to devise a way to get a critical mass in a very short time. And that's where some bright scientists at Los Alamos came up with the idea of an implosion bomb. So they had high explosive panels. That's why when you see the Trinity experiment, they're raising that thing up in the tower, it's a big sphere because it had these panels of high explosives positioned around it, and the wires go into each one, set them off simultaneously, and they squeeze the plutonium into a critical mass, into a density. That's what was required for plutonium. One more point. Real gases at high pressure and low temperature need correction factors. And that's what van der Waals did in 1873. But actually got the prize for it in 1910. Took him a while to recognize him, which is typical for Nobel Prizes. But there's a correction factor for pressure and a correction factor for volume. And if you were going to be a chemical engineer, you'd probably have to learn that thing, how to use it. But since you're not, it's just there for demonstration purposes.